We're going to be talking soon about an elastic potential energy of springs. Before we do that, we kind of need to introduce springs and specifically Hooke's law. So if we have a spring kind of hanging here from a ceiling or something, and we put some object, attach some object to the spring. Of course, the weight of the object will pull it down, and the spring will be extended. And if I measure how far this spring stretched out, that would be a certain displacement. And depending on how much weight you put on, it'll stretch out further. And so Robert Hooke was experimenting with this, and he tried to find the relationship on how much weight you would put on and how far it would stretch it. And there's two ways to look at this force. You can think about it as the weight of this object. Like right now, this weight of this object is not accelerating in any direction, so you have the weight of the object working down, but then it has to be balanced out with a force upward that the spring is pulling it, trying to pull it back. And we call that the restoring force. That's the restoring force. Now, of course, the restoring force would be equal and opposite to the weight of the object. So when you're doing this, I guess if I was doing this experiment, I would have wanted to use this force here because this is the force that I'm pulling the spring with. But Hooke decided to use this force here. They're the same force, they're just in opposite directions. So this is the restoring force, which is pointing, which is the force that the spring is exerting on the weight. So if the weight pulls that, so these are vector quantities. So if we say, okay, here's our starting point, and that's going to be 0, and I pull something, I stretch it this way. Well, that's, if we divide that as to be a positive displacement, then the restoring force is pulling back the other way, and that's going to be negative. So Hooke's law of springs was written like this. And this isn't really probably how I would have written it, but this is what he did. Force equals a negative k x. Now x is the displacement. A lot of times I write d in my classes. K then is a constant. It's the elasticity constant. It's how strong the spring is. And the reason the negative sign is on here is because when you put in, let's say you put a weight on a spring, and you put in and how far it has, for x, you put in how far it has been displaced, that would be a positive value. But then the weight that you would put in for the force, but you wouldn't put in the weight, you'd put in the restoring force, which would be equal to the weight, but it'd be in the opposite direction. You'd use this force, which would, of course, would be negative. So in for the F, you would be putting a negative force, which of course then would make the negatives cancel out, and you wouldn't really have to use the negative. So, Hooke did that for whatever reasons. I guess if I were doing this whole thing, I would have said, hey, just put the weight in for the force, and don't worry about any negative numbers. So I would have written, I guess, Herman's law as force equals k times d. So this is the displacement that the spring is displaced, and this is the force that caused the displacement, the weight of the force. So either way you think of it, it still comes out to be the same. Your K value, your elasticity constant, is always positive. It's always positive. And really, if you think about it, it's the ratio of the force over the displacement. So that means if we think about rise over run, or y over x, I could graph force on a y-axis, displacement on an x-axis, and I would get a straight linear line, and the slope of this line would be the K constant. This is force here, by the way. The slope of this line would be a K constant of the spring. So you could say, if we had let's say we put a 10 Newton force on a spring and it stretched at 30 centimeters. What would be the K constant? Well, it'd be the force 10. It'd be the force of 10 divided by the displacement. Now the displacement has to be in meters, so it'd be 0.3 meters, or sort of 3/10 of a meter. So that would end up being 100 divided by 3. It'd be basically like 33.3. And what would the units be for K? It'd be a Newton per meter. 33.3 newtons per meter of stretch. And this would be a K constant. It'd be constant for that spring, so I would always use that K value for that particular spring. Different springs are going to be tighter or looser, so they're going to have different K values. But this is Hooke's law. This is the way I technically write it. The force is proportional to the stretch, or as the way Hooke said it, tensio, however you pronounce this, which means as the extension, so the force. As the extension, so the force. So if I have force versus my displacement, it's going to increase at a constant value. So, Hooke's law. Hope you understand it.